Welcome to Traveling Waves, one of my all time favorite chapters of the year. So much fun things to think about, so many fun activities that will be able to do online. And so I think you're going to find this to be kind of an enjoyable chapter. Not real tough concepts involved in it, and moves along kind of nicely, and it's just going to be fun. All right, Traveling Waves, we're going to be talking at first just about waves in general, and then later on, we're going to be more specifically talking about sound waves. So let's get some general ideas about what a traveling wave is. And I've written a lot of the things out for you. I think probably I write a little bit slowly, and so then you're just waiting for me to catch up to how fast you've already been. So if I go faster than you're able to keep up, you can always pause me, but it will make it more efficient for you, I think, if we do it this way. Also, the reason that I've chosen this format instead of doing it off of the iPad is that I will be doing a lot of drawings in this chapter, a lot of diagrams, and I just can't do that on the iPad. So we're going to stick with this format probably for most of this chapter. Right, the definition of traveling wave, it is a disturbance that moves from one place to another. So it is a moving disturbance in whatever the medium is. Disturbance in air, disturbance in a liquid. It can even be a disturbance in a solid. It just has to move from one place to another. And there are two ways that we're going to categorize these. This first way is not as common. We won't use it very often, but you can categorize a traveling wave by the number of disturbances that are created by that event. The first one is an impulsive wave where there is one disturbance. That's all that's happened. It is one disturbance that moves through space. A clap would be an impulsive wave as long as the clap just creates one disturbance that moves. If other things vibrate as a result of it in the process of the clapping, then it may not be impulsive. But if there's just one disturbance, it's going to be an impulsive wave. A shock wave, and I'll post a video of a shock wave on the page, but a shock wave would be another way of identifying an impulsive wave. The other kind is a periodic wave, more common. It's going to be a repeated disturbance. Continuous tone is a periodic wave. If you're bouncing up and down in a pool and creating a number of waves, that's going to be a periodic repeated disturbances, a periodic wave. Again, this isn't all that common, but it is one way of designating a type of traveling wave. Impulsive, just one disturbance, periodic, repeated disturbances. And now let's talk about what a wave looks like. So I'm going to draw a wave for you here. My wave doesn't look all that smooth, but it'll do. And I want you actually to think of this as a water wave. And let's say that I am identifying a particular molecule right here on the wave. What's going to happen is that molecule will just continue to rotate at that position on the wave. The molecule does not move forward at all, but it stays in this position, laterally in that position. What it does do is it will bounce up and down, but it stays in this position horizontally. So let's go ahead and write that out. The molecule rolls in place. It rolls in place and moves up and down, but not forward. Can you think of an example in the ocean where this principle is actually seen and necessary for this thing to work? Hopefully, or perhaps you're thinking about a buoy. Some people pronounce them buoys, where it's supposed to designate maybe a more shallow place or something for ocean-going people to pay attention to. And so it's a marker in the ocean, and it will bounce up and down, but as long as it's not in a current, then it is not going to move at all, except up and down. It stays in place. That's why they work. That's how they work. They're not anchored to the bottom of the ocean. They stay there because it just bounces up and down, not forward or back. All right, so that is what a wave looks like, and that's generally the characteristic of what's happening in a wave. But, and we're going to take some videos. We work with slinkies a lot in this class, and so during this chapter, and you guys are not going to be able to do that. So we'll take videos so that you can see it. If you want to come in and get a slinky, I would let you check one out. Talk to me about that if you want to try that. They're actually pretty cool to work with. It's not a slinky, it's actually a very, very, very long slinky spring, but it looks like a slinky, just really, really big. All right, so now we're going to talk about the types of waves the features of a wave, I'm sorry. Features of a wave is that what doesn't move forward is it doesn't transfer matter. Matter does not move as a wave moves forward. Doesn't transfer matter with it. Instead, it just keeps bouncing up and down, but it doesn't move this way. However, it does transfer energy. And you can see even to my molecule, it's transferring energy, or to the buoy, it's transferring energy, because the buoy is going to be given potential energy going up, which then has kinetic energy going down. And then as it rises again, it's given potential energy, which is then converted to kinetic energy. So it is transmitting energy. Think about a wave can lift a boat. A wave can also transmit or transfer information. And we'll talk about that more in the next chapter when we talk about electromagnetic radiation, which travels in waves. But when you talk on your cell phone, that is a wave that is carrying the information from you to whoever is receiving your call. So it also can transmit data or information. It can transmit or transfer energy. By structure, if we define a wave by structure, there are two kinds of waves by structure. The first is a transverse wave, which is what I drew up here. Transverse wave is going to look like this, and I can never get them to look even unless I do it a little bit faster. That was not pretty, sorry. That's a transverse wave. The vibration happens this way. The wave itself is vibrating up and down, but the wave itself is traveling in this direction, so the vibration is perpendicular to the direction of the wave. Okay, so let's say, for example, I lay a slinky on the ground, and so it looks like this. I don't want to draw a slinky because it doesn't look like this, so I'm sorry. It is vibrating, which you can see through this picture. The slinky I can't use because the slinky is not a transverse wave, so I apologize for saying that. But let's look at this. The vibration of this is up and down, but the wave itself is going to move forward. This peak is going to move forward, even though the material that is there is going to go up and down. So it vibrates up and down, but the wave itself moves forward, not the material. Right, the other kind of wave is a longitudinal wave, and the slinky actually works like this. So what you have is you have a part where it's really tight together, and then it's far apart. And this time the vibration is this way, and I should write this here. Vibration is up and down for the first one, but the wave direction is lateral. But for this one, the vibration is this way, and the wave direction is this way. Now the different places are named. This part is called the compression part of a wave, and this part is called rarefaction. And sound actually looks like this kind of wave. It's a compression wave. And there's going to be areas of density, which is the compression, and areas of less density, which is the rarefaction. And I also have a video for that you can watch to help understand that. All right, and then I also want to talk to you about the parts of a periodic wave. Periodic wave means I have to have a number of disturbances. Remember, number of disturbances. If I have more than one, I have a periodic wave. So let's talk about the parts of a periodic wave. This looks like a transverse periodic wave. The amplitude is the magnitude of the maximum disturbance. You can think of it as wave height. So typically you're going to draw almost an x-axis through this, and the maximum disturbance would be this piece right here. It's not going to be from the bottom to the top, but halfway is the maximum disturbance. The next piece is frequency, which is, and you hear that in anything like with radios, what frequency are you at? Frequency is a term that is used very necessarily in a wave because it tells you the number of cycles. So this, from here to here, would be a cycle. A cycle, in this case, for the top one, would be from here, where I've started my compression, to here, right before I start the next compression. That would be a cycle. So it's a number of cycles that pass through a given point. In a given amount of time. We use the unit of hertz. A hertz is the number of cycles per second. That's going to be a hertz. If you have one cycle in 1 second, it's 1 hertz. A period is just the opposite of that. A period is the time required for one cycle. So hertz is cycles per time, and period is time per cycle. So you can kind of see from that frequency is going to be inversely related to period, and period is given a capital T. They're inversely related. And yeah, I'll just put on here the time required for a complete cycle or one cycle, and it is given the symbol capital T. Right, and then the last thing we need to talk about is wavelength. And frequency and wavelength are two pieces that are often put together, and it's because their relationship is very helpful in telling other pieces of information about the wave, and we'll talk about that in a moment. So wavelength is the other factor or part of a periodic wave that we're going to talk about. The symbol for wavelength is the Greek letter lowercase lambda. It has a little bit of extra at the top. Kind of looks like a tent with the tail. So lowercase lambda is my symbol. The definition of it is going to be the distance from the beginning to the end of a cycle. So this would be the wavelength for the one longitudinal wave that I drew. From here to here would be the wavelength of my transverse wave. This little bit right here, from beginning this cycle right here to the same position in the next cycle. That would be my wavelength. And I will tell you, every year I have students who tell me that the definition of wavelength is the length of the wave. That is not true, because this wave is a periodic wave, and it's going to go on and on and on and on and on. The distance of this wave is, if this is all the wave is, that would be the distance of the wave. The wavelength is just the distance of the cycle itself. It depends on the speed of the wave and the frequency of the wave. And by the way, frequency also depends on the wavelength. The two are connected to each other. A better way of saying this would be that frequency is directly related to my speed, which is inversely related to 1 over lambda. I'm sorry, it is and inversely related to wavelength. So it's directly related to speed and indirectly related to my wavelength. That made it look like I was comparing velocity to wavelength, and I didn't mean to. So that should be an and sign in there. So as frequency increases, wavelength decreases. As speed increases, frequency increases. As speed increases, frequency increases. So if that's the case, let's kind of break this down. V is equal to d over t. But we've redefined the distance as the wavelength. So another way of saying it is, it's equal to the wavelength if I am talking about this as the speed for this piece right here, over, let's see, what was my time? Time was the time of the wave, which is the period. So it's going to be over period, which is equal to lambda all over t. So I am just redefining my speed of my wave in terms that we're used to for speed. Speed is equal to distance over time. All right, well, in a wave, what is the distance that I'm talking about? Talking about the wavelength, the distance from peak to peak in this particular wave. The period is the time it takes for this peak. So I'm still talking about time, and I'm still talking about distance. So lambda over capital T for period is just giving symbols to what I've just talked about. But period is actually kind of an inconvenient way of measuring a wave, or the parts of the wave. But we also said that frequency is, or I'll put it this way, T is inversely related to frequency. So if frequency is on the bottom here, then 1 over frequency is going to be on the bottom. So it's really going to be equal to lambda over 1 over f, which is equal to f lambda. So my velocity is equal to f lambda. And we made that point over here about the inverse relationship. All right, this is my equation then. I'm going to put it this way. V is equal to f lambda. That is a key speed formula, as is this. Don't forget that we can also use this. And if this works, use this one. But if you're given this information, use this one. All right, and then I have one problem that I want to do with you. A sound wave created by a radio speaker vibrating at 300 hertz has a wavelength of 1.15 meter. What is the speed of the wave? So I'm just going to write down my knowns and my unknowns. Hertz, I told you, is a unit of frequency. So F is equal to 300 hertz. And my wavelength, the distance from peak to peak, or the beginning of the cycle to the end of the cycle, lambda, is equal to 1.15 meters. And I'm looking for V. V is equal to, I don't know. All right, so V is equal to F lambda, which is equal to 300 times 1.15, which is equal then to 345 meters per second, which is an average speed of sound. 340, 345. Depends on the conditions, the density of the air, how fast the sound is going to move. But that's a typical sound velocity. Let's talk about the units. My frequency, how did we end up with meters per second given this? My frequency is hertz, which is also the same as peaks or cycles per second times meters over 1. So I'd be left with peaks times meters over seconds times 1. But peaks is a counting number. It's not an actual unit. It's like saying I have 10 apples. Is apples a unit? No, apples are not a unit. It's just that I have counted that many things. Peaks is a counting number. It is not a unit. So that kind of cancels out in terms of my units, and I'm left with meters per second. So that's how I was able to get to that. All right, your homework is going to be 1 through 4. Your homework is 1 through 4. These are pretty straightforward. You're going to either use this equation or this equation to find the data that you need from that. All right, let me know if you need anything.